Hey everyone, welcome back to your next lesson on further GCSE mathematics. So in these final two lessons, this final section of the course, we're looking at something known as matrices. A matrix, which you've probably never seen before. It's not part of the regular GCSE syllabus, and it's not actually part of the A-level syllabus either. So it's interesting that it's specifically part of further GCSE math. So yeah, today we're looking at just introducing what matrices are, how do we work with them, how do we kind of visualize what they actually are, because that can be a little bit trickier. So let's see the plan we have today. So first of all, we're looking at how we interpret them. So this is not something that's necessarily strictly going to be something you'll be tested on as part of your exam, but it's to help you get a better understanding of what matrices actually are, which will in turn help you to then work with them. We're going to then look at how do we do some basic operations with them. So how do we add matrices? How do we multiply them, or multiply them with, say, a vector, for example? Vectors and matrices are often used together. We can see how that works, because it's not so straightforward as when we're multiplying numbers or variables or things like that. And then we're going to look at dimensions. What does it mean? What are we talking about when we say the dimensions of a matrix? And how do we use those? Like, how can we tell? Like, what can we glean from looking at the dimensions of various matrices, and what does that tell us about what we can do with them and what we perhaps can't do with them? We'll look into what exactly that means at the end. So first of all, the interpretation. So how do we interpret what a matrix is? Well, a matrix can be used, to do different things. One simple example we'll look at here is, say, if we're using a matrix to represent an image, and we're going to take the simplest possible image imaginable here, which is an image of just essentially 4 pixels, four various shades of grey here, and we represent it by this matrix. So this is what a matrix looks like. Kind of like a vector, where you've probably seen before, where it's like a column of numbers or perhaps a row of numbers inside, brackets. A matrix is then where it's not just a column or a row, it's actually almost like a grid. And here is an example of a 2 by 2 matrix, because we've got 2 rows and 2 columns. And that's all you look at GCSE level, are 2 by 2 matrices. We don't really look at anything bigger than that. You won't be like testing on anything bigger than that. So yeah, this picture here, I've kind of like encoded it with this matrix. And what does this matrix actually mean? What I've done is I've given each pixel a number based on its shade, based on from 0 being completely black and then 9 being completely white. And so you can see, yeah, that one in the top right being 0 is completely black, whereas, say, the pixel in the bottom left being the lightest one, you see it's got the highest number. And so you can kind of see how those numbers line up with those pixels there. So this is kind of an example of what a matrix can be used for, say, in like picture filtering. I'm sure that people, you guys have used filters on photos, like on your phone and things like that in the past. This is how a computer will visualize an image as like a matrix like this. And so once we've done that, we could then alter this picture by altering this matrix. So imagine, say, if I was to add 3 to each number in this matrix, so that would essentially become like this. What effect would that have on the picture? Well, if you said it would make it lighter, like this, you'd be right. Because remember, higher numbers corresponds to a lighter color, lower numbers correspond to a darker color. Or we could do, say, something like this, where we're just going to subtract 2 from the diagonal elements, and like that. So diagonal is in from top left to bottom right. And you see, if we just do that, how that will affect the picture, you see it's just the top left and the bottom right pixels will darken, because, if we're making the number smaller, it's corresponding to a darker color. Or we could do something like this, where we essentially invert the picture, where we're taking the maximum number of 9 and we'll subtract each of these numbers from that number 9. So all the light colors will essentially be, becoming dark, and all the dark colors will essentially becoming light, and it will look something like this. So when we're doing, You will see this when we do matrix addition and subtraction. This is the what you can think of it as essentially doing. Like this is like one application, but matrices, they have many applications. I'm just giving you one example here that could help you understand what it is and what we're doing. So yeah, if I now expand this to like a more real life scenario, imagine if we had a more complicated picture like this, where you can see there's many pixels. It would be like a really big matrix like this. Now, don't worry about being tested on something like this. You'll never get tested on something like this. But you see, many of those operations we were just doing, we could do the same thing on this. Like, say, if we was to invert the colors of this picture like that, it would be essentially like doing 9, subtract each of the numbers in this matrix, and they would change kind of like this, where you see all the 9s went to zeros and zeros would go to 9s and so on and so forth. So here, next time you're, filtering an image on your phone or something, you can kind of think of it like this. This is what's going on behind the scenes, essentially. This basically this matrix. So yeah, that's kind of how we could interpret addition and subtraction, because you see we were just adding and subtracting there. What about if we were multiplying by a matrix? How do we interpret that? What does that exactly mean? So multiplication by a matrix is essentially a transformation. So from the regular GCSE syllabus, you guys should already be somewhat familiar with transformations, like say a rotation or a stretching or enlargement, that sort of thing. A matrix is something that essentially applies to the entire space. So say if we have a set of axes like this, and I've drawn in grid lines like this so we can clearly see what's going on, and say if I draw in a shape like this, and what I'm going to do is I'm going to apply this matrix to this space, this set of axes. So it's like the entire two-dimensional space here is being transformed by this matrix. What exactly does that mean? Well, for this matrix, it's based on an enlargement by 2. So it'd be doing something like this, where you see everything is just expanding and becoming twice as big. And you can see that in the little square that I put there, how it becomes twice as big. Or let's take another example. So we go back to our original grid, and I've got this matrix here where you see it's kind of like the same thing, except it's got -1s on that diagonal. What exactly does that represent? Well, what I'm going to do, again, for reference, let's put in, say, a vector in this space. So a vector, again, this is something I assume you're already quite familiar with, because that's part of the regular GCSE syllabus. You know what a vector is. So you see it's like a distance in a particular direction here. What is this matrix doing to this space? What it's doing is it's effectively rotating the whole thing around. And so you see that vector then rotates with it. And let's look at one last one. So those were, a couple of simpler ones where there's just one transformation going on, but we can often combine transformations, can't we? And say with this one here, where you see there's these 2s along the diagonal, but then there's ones on the off, what we call like the off diagonal elements. What effect would this be having? It's going to do something like this, and it's kind of like stretching it, but like stretching it in a diagonal direction. Or there's a way of viewing this as multiple transformations that will happen at once. And yeah, in the next lesson, we're going to look at kind of how that would work, how you would essentially do multiple transformations in one matrix. But yeah, the key thing here is that you kind of start getting this feel for what a matrix actually is. So we've seen before, like, when we're adding or subtracting matrices, it's kind of, you could visualize it almost like a, denoting like picture or something like that. Here, when we're, say, multiplying by a matrix, it's essentially a transformation. You have this particular space, this set of axes, and you see how the axes completely change. Like they're not even perpendicular anymore in this case. And a matrix defines how that transforms from one to the other. And I can give you one real life example of this, from my own work. Like say if we had northeast, southwest like this, which is essentially like a set of axes, just forward and back, left and right, which is just flat. And maybe we're doing this on the surface of the earth to determine where we are, or something like that, or how we're going to navigate. Which is all good and well over a small area, because over a small area we can kind of consider the earth flat, but obviously the earth is not flat, it's round. And so if we were looking over a much larger area, we would have to consider things like this, like longitude, latitude, which are like curved lines. It's like a curved axis. This is a much more complicated transformation, which you won't get tested on, but um, you could essentially use a matrix transformation to convert from one to the other. So say if we was positioning in one set of axes and then we want to get our positions in the other axes, that's one real life example of where these transformations are actually would be used. So like I said, that first section, it's not something you're necessarily going to be directly tested on. It's more something I just wanted to give you a feel of what a matrix actually is and what it does. Now let's look at some actual calculations that we want to do with them. So first of all, look at matrix addition, which is relatively straightforward, and it's perhaps what you would intuitively do if I gave you, two matrices and asked you to add them. So let's say if I have this matrix and I want to add this other matrix, what do how would we do that? Well, if your instinct was telling you, well, perhaps we should just add each of the elements individually, like do top left of each and then do top right of each and then so on and so forth, you'd be correct. You essentially get something like this. So you see, we look at the top left elements first. We do 1 plus the 3. Then we do the top right, which would be the 3 plus the 2. Then the bottom left, which is the 5 plus the 8. And then finally the 7 plus the 4 in the bottom right. So this is how we add matrices. And you could perhaps imagine this as like applying something to a picture, like like what we've seen in the example earlier. If this matrix represents some picture and then we're adding some other matrix, it's like we're changing all the pixels in that image. That would that'd be like one way of sort of visualizing what's going on there. But how we actually compute it mathematically, we just add each element like this. And it's similar for subtraction. So if we were doing one, subtract the other, it works exactly the same way. We subtract each element individually and you'll get an answer like this. And you see, depending on what exactly the matrix is representing, you can absolutely get negative values as well, or you could get fractional values or whatever, any number essentially in each of the kind of slots in this matrix. So there we go. That's matrix addition and subtraction. Very straightforward. Matrix multiplication is a bit more complicated. In order to understand this, let's look back at this transformation that we had here. Remember, when you're multiplying something by a matrix, the way to visualize that is it's basically like applying a transformation. And you saw this matrix we had earlier. In order to understand this, let's consider what we call basis vectors, which are basically these vectors, this one here and this one here, where it's just basically a distance of 1 in each direction along your axes. So this term basis vector, you don't need to know that term, but that's basically what it is. It's just going at step 1 in the x direction and step 1 in the y direction. Well, you should already be quite familiar with the idea of vectors, that if we had a vector like this, it's essentially like a combination of all these individual steps, isn't it? Like the vector 4, 3 in this case is basically just 4 to the right and then 3 up. So you could write any vector you want as some combination of these like basis vectors. And so, in order to understand how anything is going to transform in this space, via this matrix, all we need to know is where do these basis vectors go, and then we'll know where any other vector would go, because every vector is some combination of those basis vectors. So if we now apply this transformation that we saw before, you see it kind of stretches it out like this. You see these vectors are now the basis vectors in this new space, in these kind of like diagonal axes that we have here. But let's say if we try and now rewrite them in terms of the original axes we had. So you see that one going in the x direction would actually be 2, 1, isn't it? Because it's 2 to the right and 1 up. So if we're now thinking of it just in terms of like a horizontal and vertical axis again. And that basis vector in the y direction is now going to be 1, 2, isn't it? 1 across to the right and 2 up. Well, that should be looking somewhat familiar. Like if we take those two vectors, those are basically the columns of our matrix. So the point is I'm trying to make here is that what you when you look at a matrix and how it's going to transform our space, what it's basically each column of that matrix is basically just telling you where do these basis vectors go. So that basis vector of just going 1 in the x direction is now going to go to the vector 2, 1. Whereas that other, basis vector just going 1 in the y direction, the vector 0, 1, is now going to go to the vector 1, 2 instead. And if you understand where those go, we can then understand where any vector would go, like the vector 4, 3. So when we're trying to transform this vector via this transformation, remember, like I said, it's essentially akin to doing a multiplication. Okay, now let's see how we can work out that multiplication using this intuition we've now developed. So if we're trying to do this multiplication, well, we know that a distance of 1 in the x direction is now going to go to 2, 1 instead. A distance of 1 in the y direction is going to go to 1, 2 instead. Well, we know that this transformation will then look something like this. So that vector 4, 3 is basically saying we're going to 4 in the x direction and then 3 up in that original set of axes. In the new set of axes, after the transformation, it's now going to go to 4 lots of this vector 2, 1, and then 3 lots of this other vector 1, 2. And so if we work that out, you're basically, you'll get what that product is going to be. It's 11, 10. So this is something you should already be comfortable in calculating. Like if we do a vector times by some number, you're basically just timesing each of the elements individually. So 4 times 2, 1 will become 8, 4. And 3 times 1, 2 will become 3, 6. And if you add those two together, again, you just add element by element. So that's one way you could work this out just completely intuitively by understanding that the columns of your matrix is basically telling you where those little basis vectors go. But it's also very beneficial to know, like to have the formal method of how we would multiply out a matrix by a vector, say in this case. So let's look at it that way as well, which has what we'll see later on. Thinking of it this way is also beneficial. So how we would formally do a multiplication, we take each row of the first matrix and then multiply by each column of the next matrix. So, well, in this case, it's not a matrix, it's a vector, but it is technically like a matrix, but a matrix with just one column. That's essentially what this vector is. It's like a matrix of one column. So what that means is we're going to get a value. The first value is going to be this. So we do 2 times the 4 and we do 1 times the 3. So we work our way across each value in that row and each value in that column. So we read left to right in the row and we read top to bottom in the column. And we multiply the elements. And similarly, the next value in this resultant vector is going to be the bottom row of the matrix times by again that column in the vector, and you see you get this. And well, then we just need to calculate out each of those elements. And if you do that, you find you'll get 11, 10 again, which you should. Whichever way you do this, it will it should get the same value. Otherwise, something's gone wrong. So that's how we can work out as well. If we're multiplying two matrices, we go through each row of the first matrix and multiply it through each column of the second matrix, and that will get us all the elements of the first row. And then we go to the next column of this matrix times that through by each row of the second matrix, and that will get us the next row, and so on and so forth. Although, like I said, we'll only ever be dealing with 2 by 2 matrices here. So let's look at an example of that. So say if we're actually trying to do a multiplication of 2 matrices, and you'll get a better understanding of how to interpret the product of 2 matrices in the next lesson, where we look at more complicated transformations. Um, so what we do is same thing. We take the first row of the first matrix, and what we need to do is we need to multiply that through by each column in the next matrix. So you see, you'll get this. And then, okay, now we move to the next column and we have to multiply that row by, through that column as well, and we'll get another value here. Then, okay, now we move to the next row in that first column. And we do the same thing again. We multiply it through by the first column, and then we multiply it through by the next column, and we get another value like this. And you could work out each of these individually if you wanted on the side, rather than putting it all in one big matrix like this. But then once you work out each of these individual elements, you see you should get this value here. So we get 1, -2, -4, -1. So there we go. That's and these are the only two cases you really need to be aware of, where you're times in a matrix by a vector, which is technically a matrix as well, but just with one column, or times in a matrix by another matrix, like 2 by 2 matrices. The same idea does work with even bigger matrices, but you won't be testing on anything like that, so you don't have to worry about it. One thing you need to be very aware of, one thing that's really, really important about matrices that perhaps you haven't encountered before with other things like variables or vectors or whatever, is that order matters when you multiply them. So say if we look at this multiplication, which you might notice are the exact same two matrices, but we've just swapped the order around. So we're multiplying the other way around. And if we do the same method to work this out, so you could try this yourself, and you should be able to get this, what you find is you get a totally different matrix. So this might be a surprise, or maybe not. If you think of it in terms of transformations, if you're already familiar with transformations, you might remember that the order of those transformations matter, and that's why it matters here as well. So that's something we need to be very, very careful of when we're multiplying matrices. What order are we multiplying them by? So that's one important thing. Another really important thing we need to be familiar with is what's known as the identity matrix. So what do I mean by the identity? So let's say if we take some random matrix A, and I've labeled this matrix A. I have this other matrix I, which is what we call the identity matrix. So what do I mean by the identity? Now, any operation we do always has an identity. So if we look at, say, the multiplication of numbers, just two numbers, 2 times 7, that equals 14. We're multiplying two numbers. What is the identity of multiplication? What it is the number 1. It's basically the number that you can multiply by that does nothing. So anything I multiply by 1, it does nothing. So 1 is the identity of multiplication of numbers. Or we could look at the addition of numbers. In that case, identity would be 0, because 0 is the number that I can add to something such that it does nothing. And in this case, with a matrix, the identity is basically another matrix with just ones across the diagonal. That diagonal from top left to bottom right is really important. So if we take something like this, so say if I do A times I, and you could work this out yourself, now that you know how to do matrix multiplication, you should get this. And, well, you work that out, you notice that's basically the same thing as A. And it doesn't matter which order you do it in either. So say if I did A times I or I times A, because I is the matrix that essentially does nothing when you multiply by it, it will still just come out to A. So that's a very important matrix that you need to be familiar with. There's this matrix that does nothing. And it has very, very important applications when it comes to finding the inverse of a matrix, which we'll look more at in the next lesson. So say if we had two matrices A, B, that, A and B that multiply to produce the identity, what that means is that A and B are essentially the inverses of one another, because doing one and then the other essentially has the net effect of doing nothing. That's basically what the identity matrix is. It's the thing that does nothing. You can think of this like in terms of functions. So surely you've seen functions like this as transformations. So say if we have like a function f of something and then g of something, and we composite them like this. Say if f of g of x is equal to x, then it basically does nothing, doesn't it? It's basically mapping x onto x. So it's done nothing. So that means f and g are the inverses of one another, like this. G of x is equal to f inverse, or f is equal to g inverse, whichever way you want to think of it. Well, yeah. Remember, matrices multiplying each other is essentially a transformation. So what this means is that B is equal to A inverse, or A is equal to B inverse. So this is typically how we use the identity matrix. Certainly at your further GCSE math, you'll be using them like this. But we'll take a deeper dive into this in the next lesson. Finally, for today, let's just finish up looking at dimensions. So I've already kind of mentioned dimensions a little bit. So the dimensions of a vector or matrix are basically the number of rows and the number of columns. So if we have a matrix with m number of rows and n number of columns, then the matrix is said to be of the size m times n. And so if we have like a vector like this, if we start thinking of this vector more like a matrix, it's like a 2 times 1 matrix. There's 2 rows, 1 column. Or we could have a row vector like this, the exact same vector, but as a row instead. And this would be a row vector with the dimensions of, essentially 1, 2. Again, if we're viewing it more like a matrix. Except, it's not, because a matrix is kind of more like a transformation, whereas a vector is not. But we can kind of use the same notation. Finally, say matrix. Okay, this something like this, 2 by 2 matrix. Yeah, so therefore it has dimensions 2 times 2. And this is what we refer to as a square matrix, when those dimensions are the same, 2 by 2, or it could be 3 by 3, 4 by 4, but like I said, you won't be dealing ones like that. But yeah, this is what we call a square matrix, because the shape of it is a square, appropriately named. So, right, to be able to perform operations such as addition and multiplications of vectors and matrices, yeah, we need to ensure the dimensions line up. So we can't just do any operation we want. It doesn't always work. So say if we wanted to do something like this doesn't work, because what we're doing is we're doing a 2 by 2 matrix, essentially adding a 2 by 1 matrix. And we know that addition, you add up each of the elements. So what do? We might do the 4 plus the 4, do the 2 plus the 3. Well, what does the 5 add to? And what does the 1 add to? Well, it just doesn't work. Like you can't do that. So that's essentially an operation you just can't do. Whereas you take something like this, we've already seen something like this, no problem. And the reason why that is because the dimensions match. We've got a 2 times 2 plus a 2 times 2. And we know we can just add up all the elements. Same thing works for subtraction. Basically the dimensions of the 2 things we're adding have to match. And yeah, you can see here we get that answer. That should be something you're all comfortable in doing now. Now let's look at, say, with multiplication. So say if we was taking that matrix and multiplying it by this vector 4, 3 again. So we're essentially doing a 2 by 2 matrix times by a 2 by 1 matrix. And you notice, following that method that we saw before, where each row of the matrix we multiply by the column vector here, well, you can see we can work that out, and you get 13 by 11. And what essentially happens here is the second dimension of the first matrix and the first dimension of the second matrix essentially disappear as long as they match. So you see here the middle 2 numbers there are 2 and 2, and they disappear. And what it does is it produces a 2 by 1 matrix, essentially a vector here. So that's what happens when we're multiplying. It's like two matrices, or matrix and vector. Those inner 2 numbers essentially, if they are the same, they'll disappear, and those 2 outer numbers will essentially produce the dimensions of the answer. But only if those 2 inner ones match. So say if we do something like this, which is the exact same problem, but we're multiplying the other way round. Well, we know already that order of multiplication matters. So if we can work this out, you're not going to get the same value necessarily. But this is actually one that you can't work out. Because remember, we're basically taking each row of the first matrix or vector and trying to then multiply by each column of the next. But each row of that vector is just one value, and then we've got to try and take that value and multiply it by the column which has two values. You can't do that, and you can see that here it doesn't work because, like, by looking at the dimensions there, you see we've got a 2 times 1 multiplying by a 2 times 2. Well, those middle two numbers, there's a 1 and a 2, they don't match, and that's a clear indicator that you can't do this multiplication. So that's what dimensions are and how we can use them to determine whether or not we can actually do a particular operation, whether it's addition or multiplication, but also to infer what are then going to be the dimensions of the answer, which is handy because then you can almost use that to, somewhat check your answer and make sure that you have done things correctly. Like if the dimensions don't line up in what in your answer, then you know you've gone wrong somewhere. So there you go. That's an introduction to matrices. So we've looked at what matrices are, how to interpret them, which I appreciate is quite tricky. So you might want to watch this a couple of times to wrap your head around it, and then how to do some basic operations with them. And next time we're going to take this a step further. We're going to look at how can we then use these operations to then do more complicated things to solve systems of equations, or we can look at how to do multiple transformations and things like that. So I'll give you a little challenge question here. So we've got this square matrix here, A, which I've just 0 minus 1 1 0. So we can raise a square matrix to an integer power in the same way how we do with, say, variables or numbers. So if we do, say, a squared, it's basically just a times a. And it doesn't matter which order you do it in because it's the same matrix. So you could do that multiplication, work out what that is. So yeah, can you work out what a squared is? So you're doing a times a. Or maybe a cubed, where you then take your answer to a squared and maybe times by a again and see what does that produce. Or you could do a to the 4, where you times it by a again. So those are things that most of you should be able to work out based on this lesson. And my question to those of you that really want the challenge here is, by observing the pattern that's going on here, can you infer what a to the power 100 is going to be? So I don't want you to work out all the way up to 100 because that would take forever. Can you see the pattern? Or better still, you might not even have to work out these powers at all. If you can kind of understand what this matrix is as a transformation, you could actually kind of infer what a to the power 100 is going to be without having to work out anything at all. So here's your challenge question here. Very well done if you can work this out. Because like I said, matrices, they can be a bit tricky. So here's your takeaways for today's lesson. I'll see you next time for the final lesson where we're looking at applications of matrices.